All right, for those of y'all who need to do the lab, I'll go ahead and run through it for you real quick. The lab was talking about heat transfer between different metals and water, and we were investigating the specific heat, which is the, let's see, where is it? Specific heat. This guy right here, specific heat. That is the specific heat, sometimes called the C sub P, which is specific heat capacity, the capacity of heat. And what that is, it is the quality of a metal or quality of a substance when you're looking at the heat equation, which you should be familiar with from chemistry back in the day, which is the mass times the specific heat times the change in temperature. The product of those three will get you the value of heat. And what this actually tells you is kind of the rate at which metal or the substance will heat up, right? So this is the rate or the amount of energy required to raise the temperature of the substance by a degree Celsius or 1 Kelvin, or increase if we're using if we're using calories or we're using joules as the rate of energy, right? So it really just depends. It really just depends on what we're talking about. But this right here is constant for any substance, regardless of how large or how small. It just tells you how quickly the heat will transfer, right? So you might notice that if you touch something that's metallic or something that's wood, even if they are the same temperature, you might feel one of them is cooler to the touch than the other, even if they're the same temperature, because of this specific heat and its ability to transfer energy from yourself to it, right? So it like steals your heat a little bit quicker. If it's something that's like a metal, it's a very good conductor of heat and electricity. All right, so let's get into it. Let's take a look at your lab, and let's actually do the lab. So this here is a bomb calorimeter, and the bomb calorimeter will be closed up when I close this here. So I'll just kind of like show you real quick. If I start it, notice the lid closes, right? And over time, we're going to see the change in temperature. Now, since the starting temperature of the metal was 20 degrees and the water was 20 degrees, um, there will be no heat or the transfer of energy due to a difference in temperature, right? So it's important to note that heat only occurs when there is a difference in temperature. If there is a difference in temperature, if the temperature of, let's say, the hot object is greater than the initial temperature of the second object, then you will have heat transfer. If they are the same, right? If I make this an equal sign instead, then you will not have any heat transfer. Okay, and this is called thermal equilibrium when this gets here, and this is actually when the temperature stops changing. So let's go ahead and reset this. So let's say that the temperature of the silver this time is 220, and I believe this is actually the this is actually your first data point. So the temperature is 220 degrees Celsius, and the mass is 120 grams. The specific heat of water, or the C of water, is always going to be 4.18 joules per gram Kelvin. Um, or if we're using kilograms, it's going to be, since grams is a thousandth of a kilogram, if we just multiply that value by 1,000, you get 4180 joules per kilogram degrees Celsius, or joule per kilogram Kelvin, right? There's no such thing as a degree Kelvin, it's just a Kelvin. And the reason why, just so you know, this works out, why the number is the exact same, whether it's Celsius or Kelvin, is because on relative scales, even though these are keeping track of different things, degrees Celsius is looking at the freezing and boiling points of water, right? So 0 is freezing, 100 is boiling. And the Kelvin scale is looking at just literally the kinetic energy of the particles. Um, each one of these, a degree of each or a gradient of each, is the exact same thing. So 1 degree Celsius, I'm writing this all wrong, 1 degree Celsius is equal to 1 Kelvin. The gradients are the same. So that's why you don't have to change the units at all, okay? Or you don't have to change the value of specific heat of water or any other thing for that matter. Okay, so anyways, so your initial temperature of the silver is 220. The mass is 120 grams. If you were converting this into kilograms, what would you have to do? You divide by 1,000, so move this decimal place over 3 times, right? So let's go ahead and start. The specific heat of silver is 0.234. Let's look at this and investigate, right? So this is, see what's happening. So notice the silver is a pretty substantial mass, right? Pretty substantial mass compared to the water at least, right? And yet you don't see a gigantic shift in the temperature, right? This is 220 degrees versus 20. It's 200 degrees hotter than the water, yet look at the final temperature, right? Look at the final temperature. It's not right in the middle. It's not even close to 220. So let's look at why. Look at the specific heat of water, 4.18, versus the specific heat of silver. This is actually its leading integer is a whole number. This is a fraction. So, I mean, you have experience with this. It takes a while to heat a boiling pot of water, but something that's metallic will heat up relatively quickly, right? Now, I want to do this exact same thing again. So notice the steepness of the curve. But look what happens if I were to not make the temperature 220, but maybe just 100. So let's look at the steepness of that curve. And do you think it's gonna reach equilibrium faster, or do you think it's going to cool down? Do you think this metal is going to cool down slower or faster? So let's look at the steepness of the curve. Looks like I forgot to pick the metal. Same metal, right? We want to keep everything constant. We have a control. The control is going to be the metal type. Or the constant. So look at that. So immediately, you might not remember what it looked like. And in fact, what I will do is I will snip this so we can actually see it. Well, let's let me keep going first. But just if you remember, it looks like it's not as steep, right? So let's see. Let's go ahead and snip this. Snip this in the bud. Okay, so I'm going to keep this here, and we're going to look at that in just a second. I'm going to go back and I'll redo the experiment here. So let's reset it. Silver, 120. Keep everything the same. 220. And we're going to compare the relative steepness of this real quick. Look at that. So I want you to finish the statement. The greater the difference in temperature, the blank, right? So let's actually look at our snipping tool here. And let's compare. All right, so let's compare this guy. You can see, you know, I can't really I'm having a hard time getting it side by side. But you can see the steepness is much, much greater here. And so it reached thermal equilibrium quite a bit faster, right? It was able, in the same period of time, it was able to cool down much more, much more. So that is that's kind of how entropy works. The more energy you have in a system, so the higher the energy, the higher the rate of entropy, or the willingness for it to become disordered, right? So that's kind of neat. Okay, so our final temperature was 56.6 degrees Celsius, and you can make your calculation from there, and your calculation is going to kind of go like this. So you want to keep track of what you're doing, and this whole lab is basically trying to see if you understand that the heat that is lost by one object, and it's usually going to be the hot object, right? It's always the hot object. That's the second law of thermodynamics, hot to cold, is going to be gained by the other object, right? So let's actually do that. So in this case, the cool object was the H2O, right? This is H2O. Hot object was the silver, which was Ag. All right, and let's actually write this out now. So negative MCAT, which I call, it looks like an MCAT, so that's how we do it, is going to be equal to the positive in here. Now, what was our mass that we had there? The mass for the water, or the mass for the silver, was 0.12, because we're making it 120 grams into kilograms, right? So 0.12. The C of silver, C of silver was what? 0.3 or 0.234. 0.234, and I'm just going to set this up just because I got stuff to do, but I'm just showing you how to work this out, okay? And then the change in temperature would have been, where did it start? 220 to 56.6. So calculate for 220. 220 minus 56.6. All right, so 163.4 was our change in temperature. So that's what the change in T is, right? I already forgot my value. I'm tired. 163.4, 163.4. All right, so this is how you would plug this in, but I'm going to go ahead and go back and just show you like how to do the algebra. So that's where the variables would get plugged into. That's how you would plug those in. But let's actually see. I erased my whole thing, didn't I? Okay, there we go. That's better. And I'm going to cut this a little short now just so I can move on. All right, so let's see. So we are solving for the, what are we solving for? We're actually not solving for any of this. We're not solving for any of this. All we are doing in this one, this is if you were to mix things together and you had to solve for an unknown in the other. But all we're doing in this is we are looking at the Q for silver. Sorry, I'm jumping ahead. We're like a week beyond this. So I'm thinking we're doing more calculated math stuff, right? So this is just MC changing T. And let's go ahead and do that. We're calculating the heat energy. So the mass was 0.12. The C was 0.234. The change in temperature was 163.4, right? Yeah, I got it, kind of. And you calculate that out, you get the heat. And what's interesting about this is that since this guy right here, should I end up with a positive value here? I shouldn't, right? So I did something kind of funny with this, right? I didn't get a negative mass, I don't have a negative specific heat. But if I expand the heat equation up here, this change in T, right? How do I calculate change in T? T final minus T initial. So what was my T final in this problem? My T final was 56.6, right? For both materials, for the water and the silver. 56.6, and what was my initial temperature? It was 220 degrees Celsius for the silver, right? So if I do that, what's going to happen? This value is going to end up getting a negative change in T, right? So if I have a negative change in T, what's going to happen in the second to last row in that first box? The change in heat energy, change in Q, should be what? Negative or positive? It's going to be negative because I had a negative change in temperature. Now look what happens when I plug this into the water side of the equation. Now the mass of water is 30 or 0.03 kilograms. The C of water is 4.18. And the change in temperature, let's look at the change in T this time. So I'm going to write it over here. For water, it's blue. Change in T. T final minus T initial. Now the T final is also 56.6. But what was the T initial? T initial was only 20 degrees, right? So this is going to end up being a positive value over here. So because this is a positive value, my change in heat will be positive. Okay. So that's about all you need to know for this. Let me go ahead and just run the other experiments real quickly. So the next one was water and gold. So let's use gold real quick, and everything's going to be the exact same types of manipulatives. Everything, the manipulated variables are going to be the same. All right, here we go. Except the specific heat of gold is 0.128. Water is going to have the same specific heat. Look at the rate of change here. So notice the specific heat of gold is lower than that of silver, right? So would it have taken more energy to heat up gold or less energy to heat up gold than that of silver? Well, if you look at the final temperature, this thing didn't have as much heat energy to transfer to the water. That's why I didn't bring it very high up, right? So think of some ways and some things that you can do to bring this water temperature up. So 41.8 is the final temperature. Okay, let's do the last one. That's going to be copper. Okay, so copper, show the specific heat of copper. Same mass, same temperature. Start this bad boy up. Much higher specific heat, right? Look at the rate. Remember, let's compare that to, and I closed it out, never mind. I was going to show you the picture of the silver I had earlier, but you can see that the steepness of this curve is much higher. And what do you know, what do you think this flat line means? What's the name of this line right here? And what vocabulary term describes this line? Well, that's when there's no more temperature change. That means they have to have the same heat energy. It's thermo-equilibrium. They have the same temperature. All right, so that's the final temperature. And that's pretty much everything you need for the lab. Okay. Sorry for any of the little misconceptions, but hopefully you watched through it without skipping around too much to kind of hear me kind of correct myself. All right, have fun.